My name is Daniel Dalland, and in this video I'll be showing you how to use the graphical user interface of a Python package called Auto-VTNA. Auto-VTNA was developed by myself, Dr. Lyndon Trecker, with the help from Professor Mimi He at the Imperial College Chemistry Department. Here you can see the preprint for this publication, where we outline how the package was developed, how it works, and what it can be used for. And generally, it is an automated version of a previously available modern kinetic analysis technique known as variable time normalization analysis. I've added some links to publications in the description for this video where you can learn more about this, but it's a part of a set of kinetic analysis methods known as RPKA, reaction progress kinetic analysis, which have been developed over the last 20 years by Professor Donna Blackmond and Dr. Jordi Burés, amongst others. So to cut to the chase, in this video, I'll be showing how to use the graphical user interface. And to access this, you should go to the Auto-VTNA GitHub repository, which is shown here. So you can download these codes containing all the datasets used in the development of Auto-VTNA, which have also been quoted in the or shown in the Auto-VTNA publication, as well as a Jupyter Notebook tutorial where you can learn how to use the Python package in Jupyter Notebook. And then there's also this package called Auto-VTNA Master. And from this, you can access a folder just called Auto-VTNA, where you have a .py file for the GUI. So if I run that with VS Code, then I can initiate the graphical user interface directly. So this is the code for it, if you have installed the required dependencies that you can also find on the GitHub. However, there's an easier way to do this, which involves following this link here to a Google Drive document that you can download for free. And I've done that already because it takes a bit of time. So if you double click on it, then a console will open, which initially will be a black window, and then you need to wait like 20 seconds. So I'll skip to that. So once the GUI has launched, you'll see all this text in the console, and we can start using the graphical user interface. So to start Auto-VTNA, you need to upload your kinetic data. And as an example, I will use table 1 ethanol, which refers to a kinetic dataset collected by Clark et al. On the azamical addition of piperidine to dimethyl itaconate. And I have linked the paper where this data has been taken from in the description of this video. So here you can see the Excel file of this dataset where you have kinetic data from different experiments separated into different sheets. Each sheet contains a time column followed by the concentration values for different reaction species, in this case the product, dimethyl itaconate, and the piperidine starting material. The column for each reaction species needs to be consistent across the different experiments. If you don't have the concentration profile for some of the reactants in some of the experiments, maybe because you didn't measure it, then you can leave this blank. Just make sure you don't set up a calculation where you are relying on these concentration values, because then you'll get an error. So if we upload this to the Auto-VTNA calculator, which is done by clicking Browse, you'll see that it automatically populates the Select Experiment window as well as the Select Normalized Species windows. And you can also see a window called Select Output Species. So first we will select all of the experiments. And since the experiments have different initial concentrations in dimethyl itaconate and piperidine, we select those, as well as the product as the output species. So then we can actually run the calculation. This means that the algorithm is trialing many different order values for dimethyl itaconate and piperidine until it converges towards the best ones, the one that minimizes the or maximizes the degree of concentration profile overlay. So if we press plot results, you'll see a minimum point here where the overlay score is lowest. And if we click on it with a left click, you can see how the concentration profiles of these experiments are actually overlapping, and it's becoming linear, which suggests that we have integrated out both the terms in our weight equation. We can also click anywhere on this counter plot, and you'll see that there's a poor overlay corresponding to the darker color. You can also right click on the counter plot to also see the monotonic fitting function, which is used to obtain the overlay score. So RMSE is basically just the error of the fit when you try to fit all the concentration profiles in the same go. So we can do the same procedure for any other data set. For example, these authors, Clark et al., also studied the azomycal addition of piperidine to dimethyl itaconate in IPA. So if we load that, we select all the experiments, we select the two normalized species, which means the reaction components that we want to find reaction orders for, as well as the product. Then we click Run again. And you can see how the algorithm is converging towards the best or the reaction orders that minimize the overlay score. Now, again, we can plot the results. And in this case, the order in dimethyl itaconate is still 1, but you have a order of around 1.6, 1.7 in piperidine, which suggests that there's a different mechanism operating in this for the solvent. And then we can click on the minimum point again to see that indeed this is what gives the best overlay, and any point away from minimum will not contain properly overlapping concentration profiles. We can also visualize the data in this Excel file. For example, if we press plot kinetic data and we press no for the time being, you can see here the concentration profiles of product, dimethyl itaconate, and piperidine for all of the different experiments. You can also show them together if you choose to do that. You can also change many of these settings. For example, placing the legend inside of the plots instead of outside. So now you can see all of them in the same figure, so to speak. You can also generate an initial concentration table, which is shown here. So this shows you what the initial concentrations value are for the different reaction species for each experiment. So, for example, experiment 2 has an initial concentration of 0.45 molar in dimethyl itaconate and 0.6 in piperidine. Whereas in experiment 4, you have the same initial concentration in piperidine, but different for dimethyl itaconate. So what we can do is to select experiment 2 and 4, and then only choose dimethyl itaconate as the normalized species. We can rerun the calculation. And now we have calculated the order in dimethyl itaconate from these two experiments. So we can plot these results as before. And now you'll see that we get a graph because we are only investigating the overlay score across different orders in one reaction species. And you can see the order of 1 minimizes the error of the total fitting function, which means the overlay is maximized at this order value. You can also press show additional information to see the intervals of order values within which you get overlay scores that are only a selected percentage away from the optimum. So by default it's 15%. If you change it to say 30%, you'll see the ranges are increasing. So this is something you can use to get an idea of how well defined the minimum point is, which again gives you an idea of how confident you can be in the calculated order value. It should also be noted that the calculated order values are numerical, and you should use your chemical intuition when judging them. So for example, here I get a value very close to 1, so it's reasonable to quote the reaction order as 1. But by including the calculated unbiased value, you also give an idea of what the data is giving you, regardless of your potential bias towards round order values. To show a more complicated example, I'd like to upload another data set, which you can find in entry 1 of table 2. It's from a study by Ben Lancaster et al. On an intermolecular catalytic asymmetric alkene bromoesterification reaction. So in this data set, you have many different experiments, a standard run, as well as different excess, which is DE, in all of these different reaction components. If you want more information about this interesting study, you can read this publication, which is linked in the description of the video. But in a nutshell, the authors monitor the formation of the product of this bromoesterification reaction over time and derive the orders with respect to the different reactants with standard VTNA. And they also found that the side product inhibited the catalyst. So to start to get an overview of the dataset, we can click Visualize Data. We can plot the kinetic data here with a concentration unit of millimolar. And we can visualize mass balance if we so choose, for example, between the carboxylic acid starting material and the product. And we can select stoichiometries of 1. Then you will generate plots like these, where you have all the different reaction components for all the different experiments that you can scroll through. You can also plot the concentration profiles of a selected species, for example, the product. So those are shown here, but it's a bit hard to interpret when there's so many different experiments. We can also generate the initial concentration table. So here you can see the standard run, so standard initial concentrations in millimolar. And these are then varied one reaction component at a time in the different excess experiments, which are abbreviated as DE. In the different excess in acid, you have lower concentration, initial concentration of the carboxylic acid component, and so on. So to begin our automatic conventional VTNA analysis, we can select the standard experiment as well as, for example, the different excess in alkene. Then we select the alkene as the normalized species. That's the one we want to find the order value for. And it's the one with which the time axis will be normalized. Then we select the product as the output species, which means we get the order in the alkene with respect to the formation of the product. Then we can run the calculation. And as you see here, we get almost an order of 1.3. And if we plot the results, this is indeed the minimum point. But there seems to be an issue because the different excess in alkene experiment reaches very high convergence. So at this point, the reaction is almost complete, but this is not the case for the standard experiment. So actually, if we look at the overlay plot for an order of 1 in alkene, it seems to be overlapping better initially. So what we can do is to modify the kinetic data by selecting the last 6 data points, or maybe 5 in alkene. Then we can rerun the calculation. And as you can see, the order we get is now pretty much 1. So if you click here, you can see the overlay is quite good. Initially, we could also remove all of this other part of the standard experiment because we don't really use it in the calculation. Okay, now we can calculate the order in a different reaction species, for example, the brominating reagent. So I select the relevant different excess experiment and the brominating reagent as the normalized species. I can run the calculation. I get a value of 1.2, and if I show the overlay score versus order plot, this is what the algorithm is telling me is the best overlay I can achieve. But actually, if we check an order of 1, we'll see that this gives a better overlay by visual inspection. So there's a problem here. And the problem is that this kinetic data has very step-like concentration profiles, which means that the data points increase, or the product concentration increases very rapidly initially before flattening out at high times. And polynomial functions are not very well suited to fit such data. However, we can get around this by increasing the degree of the polynomial from 5 to 7, because this gives greater flexibility to the fitting function, which enables it to properly adapt the shape of the data points as they are overlaying. And we can see this if we left click. So you can see here the seventh order monotonic polynomial fit has enough flexibility to properly fit the data. Another solution would be to remove the overhanging data points from the standard experiment. So if I do that, I also get an order of around 1, so 1.02, practically speaking 1, and you can see this gives perfect overlay. The minimum point corresponds to perfect overlay. We can actually now change the degree of the polynomial back to 5, and we should get a value that's also very close to 1. Now we can go over to total VTNA calculations. By this, I mean that we select several experiments with several different initial concentrations, and we select the corresponding normalized species that have different initial concentrations, so the alkene, the acid, the brominating reagent, and the catalyst. To do this calculation, it's useful to click Quick Settings. This speeds up the algorithm, which can be quite slow when you increase the number of normalized species. So I click Run. The calculation is done in about 5 seconds. Unfortunately, we can't plot the results because we have the overlay score as a function of the order in 4 different reactants. So it's very challenging to visualize this, but we can click here within the VTNA overlay plot section, generate plot, autofill, calculated values, and here you can see that the data points are overlapping very well with the calculated order values, which suggests that these are the correct values. If we get even more ambitious and we want to include other experiments such as the different excess in byproduct, different excess in the product, the same excess experiment, but I will ignore for the time being the internal standard and also this run because it has such a high initial concentration of the acid, so it's lacking a few of the initial data points. Then I can select the product and the amide byproduct also as normalized species. It's very important to use quick settings. Then I'll run the calculation and take a while, so I'll skip to the end. Okay, so now the calculation has finished and we can read off the results. So the reaction is roughly first order in the different reactants, though not exactly. There's a first order in catalyst, it's 0 order in the product, but interestingly, almost an order of -1, around minus 0.8 in the amide byproduct. So if you want to verify that these values actually give concentration profile overlay, we can click the Generate Overlay Plot button. We can shift the y-axis to 0.5 so that it's a more appropriate range. The reason the product profiles start there is that they're all shifted to start at the same value, which is what you need to do in VTNA if some of your initial concentrations are different, and Auto-VTNA does this automatically. And we can see that the concentration profiles have linearized quite well, which is an indication that we've integrated out every reaction species contributing to the rate equation. If we change any of these values, you'll see that the concentration profile overlay is diminished. For example, if we change the amide byproduct to 0, order of 0, then we also get misalignment. So this is something we can do to confirm the results that we have obtained. Okay, so that's all I wanted to say in this video. I hope this has been a useful guide to the automatic VTNA calculator, but there are some settings and probably some use cases that I haven't covered. So if you encounter any problems or have suggestions or find any bugs, then please let me know by email or create an issue in the GitHub repository, and I'm happy to help out and to make the user experience better. The Auto-VTNA public paper will soon be out, so once that's ready, I will add that as a link to the description of the video. Thank you very much.